So we proceed today with a discussion of the sampling principle and the consequences of sampling on the spectrum of the signal that is sampled. Let us recapitulate briefly the development that we had in the previous lecture. We had recognized that the process of sampling, in particular the process of natural sampling, where we allow the signal to pass through for a certain interval and then hold back the signal for the remaining interval, would lead to a loss of the property of band limitedness. Okay, we recognized that. That we recognized without reference to any analysis. I mean, we did not analyze the effect of the spectrum, effect of the process of sampling on the spectrum at all. We simply recognized that the very fact that you had jumps in the signal, right? I mean, if you had an original signal which was band limited, and if you happen to gate it, that means allow it for a certain interval and then held it back for the remaining interval, jumps in the resultant signal like this. And these jumps, so to speak, could not be constructed out of sine waves up to a finite frequency if they had finite amplitude, because that could not give you an infinite slope, right? And therefore, we needed the spectrum to extend all the way up to infinite frequency. So the property of band limitedness would be lost. What we were trying to do is to derive a precise expression for the spectrum of the sampled signal in terms of the spectrum of the original signal, right? And the way we went about the analysis was, we said, well, we could think of the sampled signal xst as xt times pt, where this was xt was the original signal which was band limited, and pt was the periodic train of pulses. And we recognized that since we were multiplying two signals in time, the spectra would be convolved. So, xsf would be xf convolved with pf. We had derived an expression for pf. In fact, not really an expression, we had derived the nature of pf, right? How did pf look? Well, pf was a train of impulses. What was pf? Pf, I mean, let's summarize it. Pf was a train of impulses located at f given by multiples of the sampling frequency, right? So, f equal to n times 1 by ts, where ts is the sampling interval. What was ts? Ts was the separation between successive startings of pulses, right? So it was the interval between pulses, the periodicity, the period of the pulses, not the duration of the pulse, but the period of the pulse, right? I mean, the pulses were of duration Tp spread in an interval of Ts, and of course naturally Tp was less than Ts, right? Now we had noted that since Tp by Ts was less than 1, we had noted that if you looked at these impulses in the Fourier domain, in the frequency domain, had strengths which were taken in magnitude from a sin x by x kind of pattern, a sinc pattern. And the sinc pattern was sampled at fractional value, at fractions, multiples of a fraction. It was sampled at multiples of Tp by Ts, and Tp by Ts was less than 1. So even in the first lobe or even in the main lobe, you would be taking multiple samples. We said that if you looked at the magnitude pattern of these impulses, impulse strengths, if you looked at the magnitudes of these impulse strengths, then the first few impulse strengths would come from the main lobe of the sin x by x pattern, right? Something like this. These were the first few impulse strengths. Okay? And what was the spacing between them? It was Tp by Ts. The spacing was proportional to Tp by Ts. Okay? Now, what had we done with the pulse? We had said the pulse is of height 1 by Tp spread over an interval of Tp. So the area contained in the pulse was always unity. And the smaller we make Tp by Ts, the more samples that we are going to have in the main lobe. The first few samples are going to get clustered towards the center. In the extreme case, as Tp tends towards 0 or Tp by Ts tends towards 0, all of them will come from near the center. So you can see that as Tp becomes smaller and smaller, that means as the pulses tend towards the impulse, you would have all these impulses in the frequency domain tending towards the same height. Can you see that? All these impulses, I'm talking about the first few impulse strengths here, but then, if Tp by Ts tends to 0, then you would be taking a larger and larger number of impulses from nearer and nearer 0, and all of them would tend to have the same height. So as Tp tends towards 0, you would have all the impulses in this train tending towards the same height. Right? In fact, we can prove this independently of this argument. But it's not very important at this point in time to worry precisely about the strengths of the impulses, but it's useful to know that even at this point, that when we start contracting the pulse to move towards the impulse, all the spectral components, all the Fourier series coefficients start moving towards the same height. Right? They all tend to become equal and have the same magnitude. Now, what is critical? You see, actually that is not really critical in our process of deriving the spectrum, though it's important to be noted. What is critical is the fact that there are impulses in the spectrum of PF located at multiples of 1 by Ts. Right? So these are the impulse strengths located at multiples of 1 by Ts. Now, as I said yesterday, this convolution that we wish to calculate, we wish to calculate the convolution of the original spectrum with this train of impulses. Let's visualize the convolution now. Let's first draw this train of impulses, a few of them. So, you have an impulse at 0, of course. And note, it is very important to have an impulse at 0. You will realize why later. this impulse at 0 frequency is very, very critical. Then there is an impulse, I will exaggerate it, there is an impulse at 1 by Ts. It does not matter whether it is of equal height or unequal height, and that is not very important. There is an impulse at minus 1 by Ts. There is an impulse at 2 by Ts. I will just show a few of them. And of course at minus 2 by Ts and so on and so forth, right? Every multiple of 1 by Ts. Now, you see, it can be considered as a sum of several functions. So we could think of it as the sum of one impulse located at 0, just one impulse located at 0, plus one impulse located only at 1 by Ts, plus maybe we could write just one located at minus 1 by Ts, and you could keep on constructing the function as a sum of individual impulses. Please note, I mean, there is a conceptual point here. I am thinking of this spectrum as a sum of several spectra, right? In each spectrum, there is only one impulse. So, this is important. I mean, this conceptual point is important. Now, because convolution is a linear operator, the convolution of XF, that is the spectrum of the original signal, with this train of impulses is the same as the convolution of XF with this sum of various functions. Of course, that is identical, that is an identity. But now we can use the linearity of convolution and state that the convolution of XF with this sum is the sum of the convolution of XF with each individual function here. Now take any one individual function here. So take an impulse located at n by Ts. Forget about what integer value n takes. So let us just take one of these functions, and that function would be a typical impulse located at n times 1 by Ts. A typical function, we call it, typical spectral component function. There is some impulse strength here. Let us call it Cn. Cn can be a complex number here. Yeah? Now for the moment, this is in the spectral domain. But for the moment, forget that we are working in, once we are mature in our being able to look at convolution as an operation independent of the domain, it's fine. But for the moment, since we are used to thinking of convolution in time, let us forget that we are working in frequency. Just for the moment, think of f as a time variable. Just though it's not correct, let's understand it that way, and then we'll realize it didn't really matter in the first place, right? What are we doing when we convolve XF with an impulse located at the point n by Ts, or at any point, at any point on this axis? What are we really doing? You see, now, what is the effect of convolving a function with an impulse? You see, it's like asking, what is the effect of adding 0 to a variable? It leaves the variable unchanged. Similarly, the effect of convolving a function with an impulse located at 0 leaves the function unchanged. Why so? Well, there's a very simple way to, maybe let me ask you. See, I claim that convolving a function, let's think in time first, right? So I suppose I have a function, say yt. I'll intentionally call it yt, not x, because let's not confuse x with this function. So suppose I have a function yt, and I happen to convolve it with an impulse located at 0. I claim the answer would be simply yt. Now, of course, we can work it out, but can we give an intuitive explanation for this? Yeah, maybe I think we should answer systematically. So, can one of you raise your hands? Who would like to answer? Okay, yeah. Where's the mic? Yeah. All right, you can speak loudly, I guess.
Fourier transformation of unit impulse situated at 0 is 1. Therefore, if...
But no. See, there is a use of the Fourier transform here. Now, you see, this is a statement independent of whether or not yt has a Fourier transform, right? So, Nikhil, yeah.
So, the impulse response if for a system the impulse response is delta t, if for the system the impulse response is delta t, which means it is you directly just multiplying by some constant, so like alpha delta t. So, corresponding to that, the output, if the input is ht, the output for the system has to be alpha times ht. So,
Okay.
here it is just
Okay, so the answer given was that, well, actually what I'll do is I'll add a little bit to the answer given to make it complete. The answer given was that if you thought of a linear shift invariant system with impulse response equal to alpha times delta t, which means an impulse of strength alpha located at t equal to 0, right? So, suppose you had a linear shift invariant system with impulse response equal to an impulse at 0 with a strength of alpha. What does this linear shift invariant system do? It simply multiplies the input by alpha. In fact, in the extreme case, if alpha is equal to 1, what does this linear shift invariant system do? It's an identity system. The output is equal to the input. What is an identity system is a linear shift invariant system. An identity system is a system where the output is equal to the input. An identity system is a linear shift invariant system, right? And what is the impulse response of an identity system? An impulse located at 0. What is the impulse response of a system that delays the input by t0? Very easy. An impulse located at t equal to t0, right? What is the impulse response of a delay of t0? An impulse located at t equal to t0. That's very easy, because what do you mean by impulse response? The response to an impulse. Now, if you apply an impulse to a system that delays by t0, it will simply delay that impulse by t0, that's all, right? So, you could think, now let's come back to our question. You see, what we are saying here is, you have now, as I said, for the moment, forget that we are working in frequency. Think as if we are working in time, and think of xf as a function f on time, and think of this also as a function of, function on time. After all, the operation of convolution can be carried out on any similar domain, right? And since we are sort of accustomed to thinking in time, it may be easier in the beginning. So you see, what can you think, how can you interpret this? I mean, when will you convolve? You would convolve, if you wish, one occasion when you would convolve is to find out the output of a linear shift invariant system to a given input. So think of xf as the input to a linear shift invariant system whose impulse response is this. Now, what does this system do by our discussion? It simply delays the input by n by ts and scales it by cn, right? It delays the input by n by ts and scales it by cn. Is that right? So, what does it produce? If you think of f as a time variable, if you put in xf into this system, out would come xf delayed by n by ts and scaled by cn, as simple as that. Is that right? This is the contribution of this particular spectral component function. Is that right? Yes? No problem. Now, convolution is a linear operation. So, the result of convolution of xf with each of these spectral component functions can now be added to obtain the result of convolution of xf with the original train of impulses. So, what is the overall convolution? The overall convolution the overall convolution xf convolved with pf is summation on n Cn xf minus n into 1 by Ts, which I shall call Fs, where Fs is 1 by Ts. Is that correct? Now we need to interpret this. We need to interpret this. You see, let's interpret one of these terms. The summation can be interpreted later. What does this term mean? It means that you've taken the spectrum, just shifted it so that it shifted it by nfs, n times the sampling frequency, and multiplied the spectrum by Cn. What is the next step here? You have added up all these shifted versions. So you get so many shifted versions of the spectrum. You've added up all these shifted and appropriately scaled versions. Right? Let's illustrate with an example. So let's assume that we have xt with a spectrum xf, which looks like this. Let's assume this height is here. Now, just as an aside, I must mention that this example of a spectrum is used very frequently in illustrating ideas, in signals and systems, or even in communication. Although you might recognize the xt which lies behind this xf, you will recognize that this xt can be obtained by convolving a rectangular spectrum with itself. Now, if you convolve a rectangular spectrum with itself, the corresponding time functions get multiplied. What is the time function corresponding to a rectangular spectrum? A sin t by t kind of function. So this would correspond to a sinc squared kind of pattern, a sinc squared t kind of pattern, right? I mean, why I mention this is, actually the sinc squared t kind of pattern is not time limited. So one cannot really generate physically a function like this. It would last for infinite time, right? But we use it as a conceptual, spectrum for various reasons. One of them is that, of course, it's band limited, as we want it to be. Secondly, at every point on the frequency axis between 0 and fm, we have a different value for the spectrum. It's the simplest spectrum where you have a different value for the spectrum at every point on the frequency axis between 0 and fm. Any other, there are several such functions possible, but they would be more complicated. They would at least need to be, functions other than linear. So the simplest possible function, which is different at every point on the axis between 0 and fm, is a linear function, right? In that sense, this is used as a prototype or as an exemplary function to illustrate certain ideas in signals and systems. Anyway, coming back to our discussion, now, you see, it immediately becomes clear to us what is going to happen when we take this and start playing around with its, when we sample the signal at a sampling rate of fs, right, and start playing around with the spectrum. Now you realize that the statement that I made earlier about the impulse located at 0 frequency comes into play here. See, suppose I didn't have, that means suppose C0 was equal to 0. What would happen? The spectrum would not, the only thing that would comprise the spectrum of the sample signal are shifted versions of the spectrum. So the original spectrum between 0 and FM would be completely lost. So it's very clear that that impulse located at f equal to 0 is very important, because that's what keeps the original spectrum in place, right? So we have C0 times xf as the term corresponding to n equal to 0. Now what is the next term? Now we'll take two terms at a time. We'll take the term for n equal to 1 and the term for n equal to minus 1. What will the term at n equal to 1 do? It will take the spectrum and shift it forward by fs. What will the term at n equal to minus 2? It will take the spectrum and shift it backward by fs. Now we can study any one of them and come to a conclusion about the other from this one. So let's take this term for n equal to 1. Now there are two possibilities here. When I shift the spectrum forward by fs, of course, see, when I keep shifting the spectrum forward, the shifted version which will create trouble for me is the one that is shifted the minimum. That's the one for n equal to 1. The one that is, the one shifted by 2fs is not such a, whatever worry I have is about this spectrum getting polluted. Polluted means that that's right. If I take the original spectrum and shift it forward, and if those shifts lie in the same zone as my original spectrum, then I have trouble. So let's visualize the situation. So visualize this moving forward. Now let's assume in the beginning that fs is very large, right? Fs is very large. So when I shift it forward, so let's say fs is very large. Now in that case, I would have this going sufficiently away. So I have, fs plus fm and fs minus fm. And the height would be c1 here. And of course, similarly for the case of c minus 1, right? So if fs is very large, then I would have the c minus 1 term coming in here at minus fs minus fs plus fm and minus fs minus fm. Height c minus 1. Is that right? Here I have assumed that fs is large. No? What do I mean by fs being large? I mean that this doesn't overlap with this, right? Now of course if fs is large, 2fs is also very large. So we are assured that the further shifts will not interfere. Similarly, if fs is large, then minus 2fs is also very large. So therefore the backward shifts will not interfere with us any further, right? Now the question is, what do we mean by large? Right? What do we mean by large? How large should it be, or how small can it be? Right? Now, what is the smallest? Now we can see from the figure. What is the smallest fs that we can allow? What do you mean by smallest? That's right. Why 2fm? What is it that we need? We need this shift. Yeah. So maybe let me ask somebody. Let's have a proper answer. So is the mic around? Yeah. So just pass the mic. Yeah. Now turn it on and give a clear answer. Right. Let's have a clear answer. What's happening here? And what do we want? And what is this large and small business?
We don't want the signal to get polluted, because this is as in if I want the signal, then fs minus fm should be greater than fm. So fs should be greater than twice fm. I don't want these two to overlap. So fs should be greater than twice fm.
Yeah, that's right. Very good. That's correct. So in fact, as Nikhil quite correctly says, what is it that we are worried about when we talk about large and small? We are worried about the original spectrum being corrupted by its shifted versions. And which is the spectrum, which is the shifted version which is most likely to corrupt it? The very first shifted version. I mean, if the first shifted version doesn't corrupt it, neither will the others. So we need to worry about the first shifted version corrupting the spectrum. When will that happen? That will happen if this tail here comes inside this tail here, which means if Fs minus Fm, now this point as you know is Fm, and this point as you know is minus Fm. So therefore, we are worried, we want Fs minus Fm to be strictly larger than Fm, which means Fs is strictly larger than 2Fm. A very, very important result, a very, very important result. A very important result in the theory of sampling. Right? What have we said in effect? We have said that the minimum sampling rate that we must have in order not to corrupt the original spectrum is twice the maximum spectral component in the original signal. We have assumed that the original signal has a maximum spectral component. The Fm here is the Fb that we talked about in our band limited signal, right? So therefore, what have we said here? We have said that it is, see, firstly we have said it is possible to leave the spectrum unpolluted even after sampling. Secondly, we have said this will happen provided the sampling rate is greater than twice the maximum frequency component present in Fm. Now, certain subtle points. Yes. We'll come to that. The question is about being able to recover the original signal from the sample signal. So we'll come to that issue now, right? But before that, we first, you see, it's very clear to us that we should not allow corruption. If we allow corruption, then of course the possibility of recovery is lost. But if we have not allowed corruption, maybe there's a way of getting back the spectrum. We'll see that later, right? But before that, certain subtle points. I said Fs must be greater than 2Fm. Why not equal to? It seems that even if it's equal to, it seems to be doing the job. Now there's a problem there. Suppose we have a mixed signal. That means a signal whose spectrum has both impulses and continuous portions. Or suppose a spectrum has only impulses. And by our misfortune, suppose there is an impulse only at Fm. What does it mean about the signal? What I am saying is, consider a signal which has an impulse only at Fm, and therefore at minus Fm, you know. Now, what signal are we talking about here? What is the signal that we are talking about here, which has only impulses at plus Fn and minus Fm? That's right, it's a sinusoidal function with a frequency of Fm. Now, that depends on the strengths of these impulses. If these strengths are both positive and equal, it's a cos function. If these strengths are both imaginary and if they have opposite signs, then it's a sine function. Well, what I mean is sine t, sine Fmt, I mean sine 2 pi Fmt is e raised to the power j 2 pi Fmt minus e raised to the power minus j 2 pi Fmt divided by 2j. So, if you have a strength of 1 by 2j here and a strength of minus 1 by 2j here, then we are talking about a sine function. If both of them have a strength of half, we are talking about a cos function. Now, you see, I am emphasizing these distinctions because this becomes important in the context of sampling. Suppose out of misfortune, you happen to have sine 2 pi Fmt as xt. Now, it's band limited by our description to Fm, right? And you happen to sample this precisely at twice Fm. So, Fs is equal to twice Fm. What will happen to the spectrum? Let's draw the spectrum to make it explicit. This is the original spectrum at Fm and minus Fm. And as I said, you to sample at Fs equal to twice Fm. So you have 2 Fm here. What I'll do is, I'll draw the shifted versions in dotted form, right? So now this shifted version, the forward shifted version, puts impulses at 3 Fm and at Fm. Do you agree with me? It puts impulses at 3 Fm and at Fm. And naturally when you put impulses together at Fm, their strengths add. And in the case of a sine wave, you can see, suppose you, again as I said now, if your pulse starts narrowing down and C0 happens to be equal to C1, what will happen? This will completely disappear. Right? When you add these impulses, it would completely disappear. So it would kill that. In fact, the whole spectrum will become 0. Now this is actually this way of eating. Right? We could show that directly in time. This is a sine omega m t pattern. What are you doing? You are sampling this at t equal to all multiples of 1 by of Ts, but Ts is 1 by 2 Fm, right? So where are you sampling it? You are taking samples sine omega m times k by 2 into 1 by Fm, right? So sine pi k, the kth sample is sine pi k. Can you see that? So what is the kth sample? This is the 0th sample, this is the first sample, the second sample, the third, and so on. So all the samples are really at the 0 crossings. Where has the problem come? The problem has come because the original spectrum, when shifted by Fs, just overlapped at the boundary. And since there was an impulse at the boundary, these impulses added together. I mean, there's a reason why I first analyzed this in frequency. You see, in time, it's very obvious what is happening. What is happening in time? You started sampling the sine wave at 0, where it is 0. And you've continued to sample the sine wave at 0. As a consequence, naturally, you have all 0 samples. Now, all 0 samples can correspond to the 0 function, which is also band limited to Fm. But unfortunately, it can also correspond to a sine wave with a frequency exactly of 2 Fm. Now, this is what, brings out this tricky issue of Fs greater than 2 Fm or greater than equal to 2 Fm. If you are absolutely certain that the spectrum goes to 0 at f equal to Fm, that means, or at the highest frequency component, that means the spectrum of the original signal is such that it drops exactly to 0 at f equal to the maximum frequency component. In that case, it is acceptable to sample at Fs equal to twice Fm, exactly. But if you are not certain about this, it is not acceptable to sample the signal at Fs equal to twice Fm. It must then be greater than Fs equal to twice Fm. And we see the reason why. Okay? A subtle point, but a very important point in the context of sampling, which one must emphasize right from the beginning. We have derived a very important theorem, and we shall now christen it. This theorem was Nyquist. And is therefore called the sampling theorem of Nyquist, the Nyquist sampling theorem. Let us state the theorem formally. A band limited signal, of course in brackets real signal, we are talking about real signals. With maximum spectral component at f equal to fb. Actually, we could write mod f equal to fb because we are talking about real signals, so it doesn't, it's symmetric. The spectrum is symmetric on the positive and negative sides in terms of magnitude. With maximum spectral component at mod f equal to fb can be retrieved from its samples taken at rate Fs strictly greater than twice Fp. Right? Taken at a rate Fs strictly greater than twice Fp. So far, we have only shown that the original spectrum remains uncorrupted when we take a sampling rate of greater than twice Fe. We have not shown how we actually can reconstruct it, but that's a very simple step. Let's complete that step, right? So this is a very important theorem. In fact, this is the basis of a whole subject called digital signal processing, where one can process analog signals or continuous time signals by using simply calculation or computation or microprocessor kind of devices which carry out sophisticated calculations on sequences of samples taken from the analog signal. Right? We will come to that later, but let us now complete this discussion by illustrating the method of reconstruction. This is the sampling theorem. Yeah? Well, maximum, what we mean by maximum spectral component, firstly, you see we are talking about a band limited signal. The moment you say band limited signal, the spectrum is non-zero beyond a certain point, Fb. And we are just calling that maximum point at which the spectrum is non-zero, Fp. We have said the signal is band limited and real. So when you say it's band limited, we agree there's a spectrum, there's a value of f beyond which the spectrum is zero. That's what we explained yesterday, right? Now we're just calling that point Fb. And we are saying mod f equal to Fp because the signal is real. So, the magnitude is symmetric. Yeah? Yeah.
If you want to take Fs equal to 2Fb,
yes.
then the function should go to 0 at Fb.
Yes, that's right. Yeah.
But if suppose we have a function like x of f is 1 for mod f less than equal to Fm, sorry, Fb, and 0 elsewhere, then also it would probably, as long as the function at minus Fb and plus Fb have the same value.
Okay. Let me explain his question a little more in depth, and then we'll address it. See, the question is, the subtle point about Fs equal to 2Fp, right? The subtle point about Fs equal to 2Fp. Now, I said that, if you happen to have, see, we are trying to, Kutubuddin has raised a question about whether Fs can be equal to 2Fp, under what circumstances. Okay. Now, see, let's try and consider situations where it definitely cannot. One situation where it definitely cannot is where you have impulses. So, impulses at Fm, right, even if there are continuous spectral components here. So, if you have a continuous it's a mixed spectrum, that means if it's a spectrum which has a continuous part and impulsive part, and if the impulses happen to be located at Fm, the answer is no. This cannot be sampled at twice Fb. Now the question is, suppose it's a continuous spectrum without impulses, and the spectrum doesn't go to 0 at Fs equal to, so you have a spectrum like this. You see, technically the answer is yes. Here one can allow Fs equal to 2Fb, because the problem here, you don't have an impulse. So, even if that Fm, Fs minus Fm component overlaps just at this one point, there's no energy there. There's no energy concentrated into that point. You see, so when I take the inverse Fourier transform, it is not affected if one point has a different value. You see, an integral remains unaffected if one point has a different value. You see my point? An integral is, operates on areas, on regions. So if one point in a function is changed, the integral remains unchanged. So in that sense, I mean, technically the answer is yes. Even if the spectrum doesn't quite fall to 0 at the boundaries, it is true that one can sample at twice Fb. What I said earlier was a sufficient but not necessary statement. I said that if the spectrum falls to 0 at mod f equal to Fb, you are assured that you can sample at twice Fb. You can sample it at twice Fb even in this situation. It's just a technical point that what you get back is the spectrum minus the correct value at f equal to Fb. So at f equal to Fb you have trouble. The spectrum gets slightly affected there. And of course, if you have impulses at f equal to Fb, it is ruled out to sample at fs equal to twice Fb. Alright. Now we address the question, how do we reconstruct? Well, actually the answer is very simple. Let's think in the frequency domain, right? We have the spectrum unpolluted between minus Fm and plus Fm as it was. So how should I get back the original signal? Simply retain the spectrum between minus Fm and plus Fm and throw out the rest. So reconstruction would be to take this excess F and pass it through a system with frequency response. So moment I say frequency response, it means that you're talking about a linear shift invariant system, right? System with frequency response HF given by the following. HF is equal to 1 for mod F less than equal to Fm, and 0 for mod F greater than Fm. And this would give me back C0 times XF. Do you agree with me? Do you agree with me? The original spectrum is unpolluted between minus Fm and plus Fm. What do we have? C0 times XF, where C0 is the 0th Fourier series coefficient of the spectrum. Yeah? So what we would get here is C0 times XF. Now I can just correct that C0 term by multiplying by 1 by C0 here. So if I write 1 by C0 here, I can take care of that as well. And I get back XF. Actually, that's hardly a very serious thing. It doesn't matter if you get a multiple of the original signal. It doesn't affect you very seriously. So one can always amplify and de-amplify. Yes.
This will also be a good way to shift the signal in time.
Yeah, let's come to that later. Now, here, we've given a method of reconstruction in the frequency domain. What are we doing? We are multiplying excess F by HF. So it's a filtering operation, right? It's a filter. What kind? Let's sketch the filter that we are talking about here. Let's sketch HF, the frequency response of this filter. It's a filter. And this is the filter that we are talking about. Right? What kind of a filter is it? We are familiar with various kinds of filters. It's a low pass filter, right? It's a low pass filter. In fact, it's an ideal low pass filter. So what is the summary of our discussion? An ideal low pass filter with a cutoff of FM, when applied to the sampled sequence or the sampled signal, will reproduce the original spectrum from the samples, right? Yes.
Does that mean if you take your initial function as the impulses, the sample impulses, and pass that?
I think the question is yeah. Let's properly ask the question. Yeah.
So if you take your
switch it on.
If you take your string, if you take a train of samples, if you take your train of samples and pass that through a low pass filter, you will get your original signal.
If you take which samples?
Your samples of x of t.
Yeah.
Pass that through a low pass filter.
Yeah.
And you have x of t.
Yes, that's exactly what we're saying here.
It's that simple, sir.
It's that simple. Yes. Actually, I'll show you it's very simple, but we'll now interpret this operation in time. You see, what is the Fourier? This is the frequency response of the ideal filter, right? Let's find out its impulse response. How will we find out its impulse response? By taking the inverse Fourier transform. Right? By taking the inverse Fourier transform. Let's evaluate the inverse. So this is HF. Let's evaluate HT. HT is minus FM to plus FM. 1 by C0 times e raised to the power j omega t d omega by, d j 2 pi f if you're working with f. Alright? Now, this is very easy to evaluate. It's simply 1 by C0 e raised to the power j 2 pi ft by j 2 pi t from minus fm to fm. So it's very easy to write this down as 2j, I mean you can do it yourself, 2j sine 2 pi fmt divided by C0 times 2j pi t. Alright? Now let me simplify this. So I have HT is, I can strike off 2j from the numerator and denominator. So I have sine pi times 2fmt divided by C0. So I'll take all the other constants outside. No? So let me write it this way. HT is 1 by C0, right? 2j has been struck out, so let me keep pi, let me keep t there, and let me forcibly introduce a 2fm here. and also introduce a corresponding 2fm here in the numerator. There is a reason why I want to write it in standard form. Please check my calculations. I think they are okay, but check them. Yes? Alright? They fine? Yeah? Now, this is 2fm by C0. Now, can we write this in standard form? It's sinc. That's right. Sinc 2fmt. Is that right? 2fm by C0, sinc 2fmt. Am I right? Yes. Now, this 2fm by C0 is a constant, right? Let's look at the other part of the function. Sinc 2fmt. Let's sketch that. Now, where will it undergo zero crossings? It will undergo zero crossings wherever 2fm, t is an integer. So, at all multiples of 1 by 2fm, right? So, 1 by 2fm, 2 by 2fm, and so on. And so on. Now, this is very interesting. This is the impulse response, right? We have, coming from the sample signal, a train of pulses, right? We have a train of pulses. But if you make the pulses smaller and smaller, you then have a train of impulses when you sample, right? You could think of those pulses becoming smaller and smaller, and they become a train of impulses. Now, what happens when you convolve that train of impulses with this impulse response? Well, we could reason exactly in the same way as we did in the frequency domain right now, right? Yes, it becomes a sum of these sinc patterns shifted. See, this sinc pattern lies at 0. But what is the result of convolution of this sinc pattern with an impulse located at, say, some other t0? It's this sinc pattern shifted by t0, scaled by the appropriate strength of the impulse. So what do you have here? You have several such sinc functions appropriately shifted and scaled by those sample values. A very dual argument, if you see, you know. What are we doing when we pass that sample, you know, what is the sample signal? It's, you know, it goes towards a train of impulses. What happens when you what happens when you pass this train of impulses, train of pulses going towards impulses through this low pass filter? You take this sinc pattern, shift it so that it lies at every impulse or sample location, and you add up these sinc patterns. We are doing this in time. Now we are doing this in time because these samples are in time. You see, you're taking these sinc patterns in time, shifting them so that their centers lie at the various sampling instants, and you're adding up these shifted versions. Now these sinc functions are highly continuous functions, very highly continuous. They are in fact analytic functions. So what have you done? You've gone from this highly discontinuous, highly functions that are extremely discontinuous, extremely troublesome, sudden jumping up and jumping down kind of patterns, to extremely smooth functions, because you're adding up several smooth functions, and that becomes a smooth function. That's what we're doing when we reconstruct. We are going from that train of impulses back to the smooth function with which we started. Why are we saying we started with a smooth function? Because a band limited function must be smooth. Why must a band limited function be smooth? What do you mean by it's being smooth? Well, the first thing is it can't be discontinuous. Why can't it be discontinuous? The moment you have a discontinuity, then you want an infinite slope at a point. The moment you want an infinite slope at a point, it cannot have a finite, it cannot have an upper bound on the sine waves that make it up. In fact, not only that, not only can the function not be discontinuous, it must not even have derivatives that are discontinuous. That's because if it had a derivative which is discontinuous, then the corresponding, you see, what we are saying then is that a sum of sine waves up to a finite frequency have comprised a function which has a discontinuous derivative. Now, when you take the derivative of a sine wave, it gives you back a sine wave at the same frequency, right? So, this problem of summing up a finite, set of sine waves up to a finite, up to an upper limit, and getting an infinite slope will apply to the derivative also. We'll continue with this discussion in the next lecture, right?